Well, I'm delighted to be here to celebrate the department and our profession. It's a pleasure to be here to give you some thoughts on information technology and the future, as the previous panel has talked about. But I'd like to give you some thoughts on the color and size of information. Okay, so what does color mean? The color of information is really referring to the wide range, the very broad range of electromagnetic waves that we use in electrical and computer engineering to control, communicate, process information. And it goes all the way from tenths of meters to the nanometer range. Right? It's very, very broad. In the past 50 or 100 years, our profession has developed some fantastic technology, fantastic innovation, right? You look at all the devices, all of the technologies in our profession that has been generated. Many of them our alumni, our department has made significant contributions, and it just has a broad range of applications, right? Communications, it has cell phone technology, it has security, X-rays, just a number of applications that have made a significant impact in society. You know, it's very interesting that 35, 40 years ago when I started graduate school or joined Delaware, a lot of those items were not there. You know, a lot of holes there. My kids would tell me it's very sad that I lived in that time. But look at the difference that 30 years have been made in our profession, from lots of impactful technology to something that didn't exist before, right? So that's what I mean by color information. The color of information, or the broad spectrum of technologies in waveforms that we deal with. In my own experience, I'll tell you a little bit about what we do in the group and my students that I work with is in imaging. In imaging, I work in the area of spectral imaging, and I'll tell you some really interesting facts about spectral imaging that you may not know. Spectral imaging is a type of vision that you see, as you typically see, but has many, many more wavelengths than like you and I see. We see in red, green, and blue, but spectral imaging looks at many, many more bands. And the key is to find the bands that make a difference in vision, right? So in the military, it's important to go from, say, the visible bands to the near infrared, because you can see at night, right? Or if it's cloudy or foggy, then you can go to short infrared, because then you can see through clouds. So picking the right bands is critical for the application. One that is fascinating, an application that's fascinating that I think is going to have a humongous impact in health, is the so-called spectral surgery. And I'm not sure if you can put the video there, this video. If you can click the video there on the slide, please. This is a technology that they can insert some biochemical compounds into a patient to direct that biochemical compound where the tumors are, and they become activated. So by looking at the green spectra, you will see where the tumors are. And that has a humongous impact on surgery. And surgery, as you know, if you take too little or too much, it's a huge impact. So by doing spectral imaging in surgery, it's just going to change fundamentally the way that surgeons and surgeries are done. It's just one application of how selecting a spectral information makes a big difference. In our laboratory, one of the things that we're doing very recently, as we're participating in this Intel Center of Experiential Computing, and my research group is looking at time-of-flight cameras, and I'm not sure if you've seen those, but they're just fascinating cameras that can tell you depth. Right? So rather than take a picture, you take a depth image. This is an example where you illuminate the scene, and by the phase change on the illumination, you can tell where the pixel is in 3 dimensions, right? So you have something like that. And you have many devices like a kinetic that have tried to combine depth and RGB images to create a better information. But what we're doing here is we would like to tell you not only where the pixel is, but what material it has. So rather than have a camera that can tell you where it is, where the pixel is. I would like to tell you that pixel is a human tissue, it's clothing, it's metal, and so on. So the idea is that we want to create a camera that can tell you the depth, but it can tell you multispectral components so that it gives you the information of material. And this is a testbed camera that we have developed, and the program is a single aperture system, illumination, broad illumination, and a scene that looks like that. Then you will have a broad spread of information, like the depth map in the many 4 bands looked at there, but you can have many, many bands in the output. There's another project that we have. It's that I think it's really fascinating, that has implications in homeland security and biomedicine. Is when you go to the doctor, typically you get a CT, computerized tomography image that looks for the density change on the subject, right? But many times the density doesn't give you information. You know, there are many objects in here that have the same density, but can't tell you about the material. Is it an explosive? Is it a plastic? What is it, right? So if you look at the spectral characteristic of the X-ray, then you will be able to find information about the material. And that's some information that is used currently in airports and so on. Tomography is very difficult, they don't do it. And in medical imaging, it's very expensive because they rely on photon counting detector. So some of the things we're doing is creating these devices with coated aperture arrays that put different materials in the coated apertures by which you're modulating in spectra and amplitude before you collect the energy, but we're using very cheap, inexpensive integrating detectors. Based on that, you will be able to reconstruct the whole image of different energy levels and can get the information at large. So these are just examples of how color in the electromagnetic spectrum is giving us information, right? So how does this relate to the size of information, right? 30 years ago, 4 years ago, I think one of these previous talks were addressing how information processed by electrical engineers in mathematics and the availability of big mainframe computers created this new science, this new, I guess, discipline of computer science and computer engineering, right? This is what we are here today, computer science, computer engineering. We're seeing the same phenomena, but in a very different scale, in a very different aspect. We have technology in mathematics, very high computing, high computation systems, communications, sensors, signal processing, machine learning, and they're coalescing into something that we have this big computational power to understand the information embedded into these colorful data sets, these massive colorful sets. So I think this is where things are merging, and I think that's a very important area for information technologies. So I guess the final thought I wanna leave with you is that in information technology, there's just a big opportunity, a big bright future for information technologies and the things we do. A lot of promise for new students, new faculty in the department that I think will have a tremendous impact in the future of society. So the next talk in the future of computing, I guess, is Andy, that will continue with this theme. And I don't think there's a key, the format doesn't have answering questions, so maybe at the end of the talk we can chat more. Thank you.